Welcome to Far Out Up Close. What does that mean then? What are we talking about? Well, we're talking really about the big questions about our place in the cosmos, how we perceive and how we visualize that, and how that's changed over time. How we make sense of this multi-dimensional universe that we live in, most of which we cannot see. And then our search for life elsewhere and where we're likely to find it. So all that in the next hour. Our speakers this morning are fantastic. David McConville is president of the Buckminster Fuller Institute, and that pulls together really design, art, and technology to develop strategies to address global challenges. He thinks big thoughts. You can see him thinking big thoughts. He's also co-founder of the Illuminati design and engineering firm that produces creative installations, like you can see in the Buckminster Fuller Dome here on the campus. Our second speaker is Charles Alcock, director of the Harvard-Smithsonian Center for Astrophysics, a professor of astronomy at Harvard University, and lots more besides. Many other things he does. He's also worked on and is working on some of the world's major astronomical programs. So we're going to talk about our place in the universe. How we're going to do that, we're going to have presentations from both our speakers here. David will speak first, and then Charles. Then I'll ask them a few questions, and then I want you to ask a few questions. We have a decent amount of time at the end. So without further ado, please welcome David McConville.
So Richard asked that we start off by making everyone feel really small, right? This is what we excel at, visualizing space data. So we'll start with a sped-up version of this movie called The Known Universe, created at the Hayden Planetarium, where we're going to zoom through what's called the Digital Universe Atlas, where we start off, this is usually quite a lengthy presentation. We're going to do this in 1 minute. We start off on the planet at the Himalayas. We start to see all of the satellites currently orbiting our planet, the man-made satellites. And as we start to pull out, we're going to start breaking all known laws of physics with regards to speed. So we're going to pull out to the moon. You're going to see at the bottom here the speeds that will be going. We see the entire solar system at 1 light hour, 1 light day. We start to see the constellations come into view. As we get further out, the constellations become distorted because it's a 3D atlas of the stars. We see our own radiosphere, our radio footprint in outer space, our own Milky Way, our home galaxy, these surveys of all of these other galaxies in the cosmos. And then eventually we get out to the very edge of what we can observe, our cosmic horizon, which is called the cosmic microwave background. The light leaving the Big Bang. Got that? Okay, good. Could we dim the lights a little bit? That would be great. So for the next few minutes, I'd like to explore how we go about mapping and modeling our place in the universe, and more importantly, what efforts these initiatives really tell us about ourselves. For instance, the Hayden Planetarium calls this the most complete and accurate 3D atlas of the universe ever constructed, but it's not simply an atlas of what's out there right now. It's far more complex and interesting than that. It's primarily constructed from data sets collected from telescopes, probes, satellites that technologically essentially extend our senses, giving us unprecedented insights into our cosmic environment. And these probes and satellites scan different electromagnetic frequencies, right? And so they then colorize those. We normally can't see them, these invisible wavelengths. And the scientists and artists that are doing this are essentially making the invisible visible, as the title of the panel suggests. But these are also combined with mathematical simulations. They're done in computers like this. This isn't one in the Digital Universe Atlas, but it's just by way of illustration. These are galaxies colliding over the course of hundreds of millions of years. And similarly, this dark matter simulation, visualizing the amount of material that should be present in the cosmos based on the gravitational forces that we observe within and between galaxies. Exquisitely aesthetic pieces, I must say. And there's also a significant amount of what you might call fantasy or science fiction within the Digital Universe Atlas, since it simulates flying through a 3D virtual world at impossible faster-than-light speeds. Many of you might be familiar with this from Charles René Eames' classic film Powers of 10 from 1977, and my favorite rendition being the Simpsons intro from 2005. Pretty much says it all. So this has become a recurring trope when we talk about space, how we zoom across all of these scales of space and time. But we humans have been developing these kinds of visualization tricks for a very, very long time. The ability to visualize and record relationships between patterns in the sky and life on Earth has really been essential for our species' survival. These visualization techniques really enabled our ancestors to understand fertility, timekeeping, navigation, hunting, agriculture, all of these things that were necessary for synchronizing with the cycles of life across generations. And these tools really provided critical orientation, enabling cultures around the world to make sense of the overarching context of existence. So this is really nothing new, this fundamental impulse. But by the dawn of the European Enlightenment, the development of linear perspective seemed to provide the possibility of visualizing a kind of God's eye view, an objective view on the universe. And the invention of the printing press eventually enabled new visions of the cosmos, particularly the sun-centered vision of the cosmos that we all know from Copernicus, to be widely disseminated. So these visions could actually be shared around the world. And the creation of telescopes, of course, provided a way to empirically verify some of these new ideas, providing profound new insights, helping to establish the importance of scientific methodologies. But today, our visions of the cosmos have been most profoundly shaped by the new technologies emerging over the past 50 years. In particular, in 1957, Sputnik 1 was launched, as you all know, the first artificial satellite, which really launched the dawn of what we now refer to as the space age. And since then, we've had all of these kind of spectacular visions of space exploration that have profoundly influenced how we perceive our cosmic environment, painting pictures of prospects and promises of humanity's future away from Earth. Right? And this eventually resulted in enough excitement and enough imagination for the successes of the Apollo missions that inspired the global imagination like never before. And many of the inspired childhood fantasies of people growing up in the 50s and 60s have even been realized in our lifetimes. Particularly, amazingly, we've been to Mars. We've seen this through the eyes of robots in a single generation. It's extraordinary. But just as importantly, we've actually found that Mars is extremely inhospitable to human beings. So it's little surprise that we're on the hunt for planets beyond our own solar system that might be a little bit more like Earth. And in the past few years, it even appears that some of these distant planets orbiting other stars could possibly have liquid water on the surface. And this has some folks rather excited.
Now, the astronomers are calling their discovery a Goldilocks planet. Not too cold, not too hot, possibly just right to sustain water and perhaps life. And it's just nice to know that if we screw this place up badly enough, there is some place we can all go.
So, this is incredibly exciting news, but what Brian Williams doesn't clarify and possibly doesn't understand is the actual distance of these exoplanets. The one that he's referring to, it's called Gliese 581g. It's 20 light years from here, which is about 117 trillion miles. So to put this in perspective, if we can imagine the Earth as 100 pixels wide on this screen, the moon would be around 3,000 pixels away and 27 pixels wide, so like 3 of these screens over there somewhere. And at this scale, Mars at its closest would be over half a mile from here, right? If Mars were that size. And Gliese 581g is around 100,000 times further than Mars, right? So if we shrunk this planet down to this size, it'd be about at least 50,000 miles away from here. In other words, it would take us hundreds of thousands of years to get there with our current propulsion technologies, which is actually longer than Homo sapiens have been a species. So, there's this notion of us going somewhere else, but what this actually implies is that if we're ever going to get outside of the solar system, the only way is if we don't screw this planet up. Because something rather unanticipated happened on the way to the moon. Photographs taken by the Apollo astronauts radically transformed how we perceive our home planet. These so-called whole Earth images show a fragile, interconnected world without political boundaries, right? Many of you, I'm sure, were profoundly impacted by this. This was all a little bit before I was born, but these images really only show part of the story. The fruits of the space age have enabled us to study our home planet in amazing new ways, providing profound insights into the impacts of human civilization. We've seen this footage most recently from the International Space Station. It's one of our eyes in the sky, really, that give us intimate views of our planetary system, suggesting that the design of global economic and physical infrastructure is radically altering Earth's ability to support complex life here. The interconnectedness of these global phenomena can now be made visible, like this animation that's showing the flow of black carbon from factories and fires all over the world. You can see what's happening in China is absolutely affecting what's happening to us. So there are no boundaries within the atmosphere. We can even see the impact over time, like the accelerated deforesting of Brazil over the past 40 years. This is a visualization from the NASA Scientific Visualization Studio. Just watch the time up in the corner. And these impacts aren't just limited to Earth. The space age has also resulted in debris from numerous objects that we've been launching for the past 50 years. According to NASA, there are currently around 21,000 orbital debris larger than about 4 inches or 10 centimeters. Smaller than that, there's over 100 million of these trajectories flying around space. So in short, in a lot of ways, we're actually living on this planet like we actually believe we have somewhere else to go. Right? According to the Global Footprint Network, we've been going into ecological debt every year for the past 4 decades, exceeding the capacity of Earth's ability to regenerate the resources we're using. But at the same time, these eyes in the skies have allowed us to better understand the cycles of life here on Earth. Our planet is far more than just the third rock from the sun or a pale blue dot. It has the only living, breathing biosphere, the layer of life enveloping the planet that we found in the universe. And this is showing the net photosynthesis happening in the land and the oceans around the planet. And we can also visualize interconnections between oceans and land and atmosphere, starting to understand these dynamics intuitively and in entirely new ways. And we can even see that the Earth's magnetic field, and this was one of the first real discoveries when scientists first started getting together to study planetary phenomena, is deflecting the solar winds of the sun. It's keeping our atmosphere from being blown away. It's essentially like our own personal force field. And this is helping us to understand that the whole system truly is more than the sum of the parts that we could just understand through any single discipline. And as we look for habitable zones elsewhere, we're reminded that the Earth is the only planet in the habitable zone of our own solar system, with the necessary temperatures to support abundant liquid water, the so-called Goldilocks zone. And what I'm particularly intrigued by is even this familiar model of the solar system, which I know you all recognize, is outdated by centuries. We know that the sun isn't static. It's orbiting around the galactic core of the Milky Way at around about 500,000 miles an hour, with us in tow, right? We are all already astronauts, a term that literally means star sailor, right? Our planet really is a living spaceship sailing around the sun and galaxy at these incredible speeds. And this is what Buckminster Fuller was talking about in 1968 when he wrote about all of us being astronauts aboard Spaceship Earth. He realized that humanity's long-term success would require us seeing our home in many of these radically new ways. So perhaps the ultimate lesson of our visualizing our place in the cosmos these days is that Earth is actually the ecological center of our universe. That if we truly want to reach for the stars, we need to be developing multi-generational strategies for true homeland security, right? We have to build a resilient and regenerative human civilization. Because the most profound insight of modern science in many ways is that our imaginations enable us to become aware of the fact that every single one of us is the universe becoming aware of itself after almost 14 billion years of cosmic evolution. Every single one of you is something the entire universe is doing right now. And by using these visualization tools, we can rapidly start to comprehend these critical interconnections and cultivate our capacity for long-term and complex thinking, something I think we need more than ever within our educational system. And if you're interested in exploring what all of this means interactively, I invite you, particularly what it has to do with what Yo Ma was mentioning the first day, moving from STEM to STEAM, incorporating art and science, and looking beyond just individual disciplinary boundaries, but understanding truly the big picture context of education. I invite you to come down to the Buckminster Fuller Dome, which is right behind Pepke here, around 1 o'clock. My colleagues and I from the Worldviews Network, some extremely gifted storytellers and scientists, are going to be exploring what all of this means, and we'll be happy to let you fly around the Digital Universe Atlas by yourself. Thank you.
Okay, thank you very much, David. I'm sure you've got questions. Keep thinking of these questions. We've got more questions being raised now by Charles Alcott. Please welcome Charles to the stage. We're going to talk a bit more about life.
So I want to take a moment here with you to explore the notion that life did not have to come about. And furthermore, I'm going to argue with you in a few moments that if we look at the early universe, and we've actually got a lot of information about the early universe now, it was actually pretty unpromising for life. So let's talk about what that means. So I thought I'd start out with this image. This is tropical rainforest in Panama on an island called Barro, Colorado that the Smithsonian studies intensively. And it's a wonderful, rich, diverse environment. It has a density of species diversity that's 10 or 20 times greater than would be found in, say, some of the forests around us here in Aspen. And when I'm walking through this marvelous environment with my astronomer mindset, I ask, what do we actually have to have in order for this to become possible? And at its elements, all life really depends on having a warm place and a range of chemical elements. A great deal of other things have to happen for life to come about, but without the warm place and a range of chemical elements, none of this would have come about. So let's go back and see what that really means. Actually, maybe we could turn the sound down for this presentation. So this is our sun. I presented it in a way that picks out the solar flare activity, so you can see the storm activity on the surface of the sun. And as Justin Casper, who's at this festival, has made clear, those storms can be very damaging to telecommunications and power supplies on the Earth. But fundamentally, the sun, which is a relatively ordinary star, is the source of all of the warmth for our place. And here's our place. We all love this image for all the right reasons. But from a cosmologist's perspective, this is quite remarkably dense. If you ask if the universe were, all the material in the universe was just smoothed out to a uniform density, and then you tried to collapse together enough material to form a planet, how much volume would you have to sweep up to find one Earth? Well, in fact, this is the amount of material that would occupy a sphere 57 light years in radius. The universe as a whole is extraordinarily dilute beyond imagining. And for the more mathematically inclined, the compression factor is 6 followed by 32 zeros. The Earth is this much denser than the universe at large. So this means that our place, our planet, is profoundly special in cosmic terms. So we've talked about warm, and we've talked about place. Now let's talk a little bit about chemistry. And I'm sure every one of you remembers with fondness and pleasure the last chemistry class you took. But James Watson, in his classic textbook, The Molecular Biology of the Gene, started out with cells obey the laws of chemistry. Without chemistry, there is no life. And in particular, on this periodic table, I've just highlighted a few elements that we all know are critically, centrally important to everything that's going on in this room. Without carbon, there would be no carbon-based life forms. Without nitrogen, there would not have been that tropical rainforest. Without oxygen, we wouldn't have the oxygen to breathe in our atmosphere. We need iron in our blood to get the oxygen around. And without the calcium, we wouldn't have calcium in our bones. We would not be supported. Cells depend, life depends on chemistry. So now let's look at this in cosmic terms. Actually, excuse me. Yes, so now let's go back to the beginning. And I'm going to talk a little bit about the Big Bang. And you've all heard about the Big Bang. Many of you probably heard Brian Greene at this festival. I'm not going to go all the way back to the catastrophic explosion that occurred at the very beginning. But by about 400,000 years, we actually have a great deal of observational evidence for what was going on in the early universe. And so I'll talk about the universe in snapshot form, starting at around 400,000 years. And going back to chemistry, it really didn't look too promising. The only chemical elements that were present in the universe at 400,000 years were hydrogen, helium, which is a fabulous element, but it's awful for chemistry, and a very tiny smattering of lithium. There was none of those elements that are so critically important for life. And in particular, there was no carbon at all, no nitrogen or oxygen at all, no iron or calcium. So let's go to the warm place part of the story. Well, we actually observed the radiation that was left over from the Big Bang. And we've got a pretty good image of what the universe looked like at around 400,000 years. And I was trying to come up with a good way of visualizing it. And the temperature at that time was about 5,400 degrees Fahrenheit, which is not very different from the temperature of a tungsten filament in a classical incandescent light bulb. So let's just zoom in on that filament for a moment. And this is crude, but not a bad representation for what the universe looked like at 400,000 years. It was about this bright, about this color, and there was no place in it. It was all smoothed out, except for very tiny fluctuations at the few parts per 100,000 level. So what happened next? Well, it started cooling off as the universe expanded. And interestingly enough, at about 14 million years, it cooled down to the temperature of Aspen on a sunny afternoon. And in fact, it remained in, quote, the habitable zone of temperatures for a little over 2.5 million years. But nothing happened. There was no place. There was no chemistry going on. So what happened next is that the universe continued expanding, continued cooling, and became profoundly dark and entered in what we call the cosmic dark ages. Now, we're supposed to bring the lights down at this point. Thank you. This is a dreadful simulation of how... This is a terrible simulation of how dark things actually got. Of course, there are fire marshal regulations. We have to make it possible for you to get out. But it was so dark, it was darker than any darkness we can achieve in a physics experiment in a deep mine today. There was no light at all. It was cold. And there were none of the wonderful chemical elements. So that's what I meant at the beginning, when it was just unpromising. And it raises the question, why is there any life in the universe at all? So this is where the interaction with the dark side plays a stunningly important role. So we're going to have to come back to a little bit about what we know of the makeup of the universe today. This is just a snapshot of images, a nice eagle, an aspen, the Earth, some galaxies. These are all made out of the material that we understand, the chemical elements of the universe. But as you've almost certainly all heard, the known universe comprises a little bit less than 5% of the total material content of the universe today. We're not the mainstream in the universe. And I like to think of this as the chemical version of the Copernican revolution. Not only are we not at the center of the universe, we're made out of the minority constituent of the universe. The rest of the stuff is made out of, as I'm sure you are all aware, the dark matter and the dark energy. Profound mysteries of modern cosmology and astronomy. So dark energy doesn't play a significant role in the story I'm telling here, so I'm not going to talk about it any further. But the dark matter, and there's more than 5 times as much of this dark matter as there is of ordinary matter, is what is primarily responsible for taking that dark, cold, featureless, lifeless universe and producing the rich diversity of structures, chemistry, and life that we see today. So how did that happen? Well, we don't have observations of this critical phase. We don't have observations of what took the universe from this dark ages phase into the era of stars and galaxies. But we have simulations on computers. And this was made by a colleague of mine, Mark Vogelsberger, in Cambridge. And what you see here is that the dark matter flow, responding to the force of gravity, forms these filaments and nodes, and then the ordinary matter is attracted by the gravitational attraction of the dark matter and falls into the gravitational potential wells produced by the dark matter. But the dark matter is what started this process moving. So you can see in the top corner, we're getting up to about 2.5 billion years now. Now, you can start seeing little explosions. Those are a series of supernova explosions. This is the universe that lit up. This is the universe that produced all of the chemical elements. So there's a great deal going on here. I'll just take a moment to expand. The dark matter, responding to gravity and to the small irregularities in its distribution, started forming dense clumps and filaments. The ordinary matter, this minority constituent, was attracted gravitationally to those dark clumps and flowed in. And as that happened, stars were formed in those clumps, and galaxies of stars were formed. And the stars produced the chemical elements that we all depend upon today. So that brings us back to chemistry. With the exception of the hydrogen and the helium and the lithium, all of the chemical elements in the natural world today were made in stars. Every one of those elements, except for the hydrogen and the helium, were made in stars. Those stars would not have come into being if it had not been for the influence of the cosmic dark matter. And this led to the spectacularly beautiful universe we live in today. This is an image, it's called the Hubble Ultra Deep Field. It's the deepest image ever taken with the Hubble Space Telescope. Every little speck of light you can make out in this image is a galaxy with over 1 billion stars. Some of the larger galaxies in this image have 100 billion stars. So the universe transformed from this unpromising, cold, featureless place to a universe full of chemical elements and with plenty of stars. But does it have plenty of planets around those stars? So let's come back to our Earth. It's an unusual place, but in fact, we're finding lots of other examples around other stars. And this is an image of the beautiful and famous Kepler satellite, which has detected vast numbers of planets around other stars. And this image that was produced by our colleague Dan Fabricki illustrates graphically a significant fraction of the Kepler planets. And this is all to relative scale. So you can see there are systems where the planets are very close and they're whizzing around very quickly. You can see there are systems where the planets are further away from their stars, so they orbit more slowly. You can see multiple planet systems like this one, where the inner planet is going faster and the outer planet is going slower. You see a range of sizes of the planets. Now, those are they're to relative scale with each other. We see large planets like Saturn and Jupiter, but we're also finding in the Kepler data smaller planets, not quite yet like the Earth, but closer and closer to the Earth. And we're finding planets, as we just heard from David, that are in the promising Goldilocks zone, where the temperature is just right for life. So things really did turn around. And what I'd like to do now is address where we're going next. Because I've told you a couple of very important things that are not actually based on observations. I said that stars came into being in the transition from the end of the Dark Ages, as shown in that video. And that must have happened at about 500 million years. We can't see back that far with the telescopes we have today. Additionally, a number of us have commented at this festival that some of these planets are very promising locations for life, but we don't have the capability of studying those planets directly. So a number of us are embarking on adventures to build next-generation telescopes that will help us collect the observational data to actually confirm the ideas that I've been describing to you here today. This is a telescope that the Smithsonian and 10 other partners, it's an international partnership, are planning to build in northern Chile. The primary mirror is composed of 7 big segments shown here. Each of those segments is over 25 feet in diameter. It'll be a remarkable feat of engineering. And the reason that telescopes get bigger is that we keep looking further and further away or at smaller and smaller objects. So bigger really is better if you can actually manage to build a telescope. So this is an extraordinary time to be an astronomer, because these profound questions having to do with life are on the verge of resolution. And so let me come back to Earth, if I may, and take a more local image. This is a photograph taken very close to us here. Beautiful forests, interestingly, with much less species diversity than you see in the tropics. But I'd like to leave you with this sentiment. The origin of life is fundamentally an astronomy story. Thank you.
Okay, if we can have the lights up. Excellent. David, if you'd like to join us. I told you we'd make you feel small. If you could think of sure, you've got loads of questions. It's very difficult to know where to start. We've talked about these really big subjects. I'm interested, both David and Charles, how these images from the universe and how these have placed us, given us a position in the universe, how that's changed us. Has it changed us?
Always changed us. Is this on?
Yeah.
All right, good. I mean, I think it's been such a fundamental part of the human existence that we're constantly being transformed by the visions of the cosmos. And I mean, I'd love to hear your take on what's happened in the past few decades.
Well, I think the images are profoundly important to everything that we do, because understanding comes from being able to absorb the data that we gather. And some of these data sets are extraordinarily complicated. So what we call scientific visualization is an important subdiscipline in our field now. So images rule.
What I'm intrigued by, though, is all those images, it's once again puts us at the center of the cosmos, doesn't it? Mm. It's like the original, the ancient idea that we're at the heart of everything.
Welcome to the paradox of self-consciousness. I mean, so astronomers call it our observational center, right? Because when we're looking at these far-off objects, we're actually receiving photons. So we use the language of looking at things far away, but it's just that the sensitivity of our instruments are becoming greater and greater and greater, and we can calculate the relative distance. But as a consequence of that, as we collect everything, because of our instruments being here on Earth, it's where we live, that becomes by default, when you try to map the observational data, the center of everything. But this is what I was referring to in the talk. It's actually more complex than that, because it's not just the observational center. It happens to be the one place we know of where self-consciousness has had the necessary conditions to arise and to come up with ideas of things like the universe and telescopes and iPods and everything else. And so I tend to think of it more in terms of, instead of just an observational center, it is more of our ecological center, not the absolute center in a spatial sense of the universe, but from our unique perspective as a species doing all of this research, it's a profound realization that we're extremely situated here. And we haven't managed to go anywhere else yet, and we probably won't for quite some time.
We'll come back to that in a second. But you were talking about life. There are so many things that have to have happened for us to be here. Does that mean that life is rare?
Well, we don't know, but we don't think so. Because the series of events that I described occurred on a cosmic scale. So we've compelling reason to believe now that there are very large numbers of other planets very similar to our own. And we don't yet actually have a very large number of planets that are very similar to the Earth, but we're getting very close to finding those. So the circumstances that hold here probably hold in very many other places. Now, what we don't know is once you set it up, once you create a planet at the right temperature and you have a bunch of water, how commonly does life occur? And that's something that's going to be addressed in part by astronomers working with telescopes that we're only now beginning to design and build, and in part in the laboratory. People are doing experiments to try and synthesize the first stages of life in labs. And it'll be the combination of those two that lead to the plausible answer to your question.
I just want to come back before everyone else has a chance to ask questions. You talked about, you sort of mentioned it in passing, generational travel. So we would leave the Earth, we would go to where Brian Williams was talking about, Earth 2.0 or whatever. And that would be a major, massive, world-changing undertaking. Is it even possible? Are we capable of that?
No. Not until we get this one right. Because there have been experiments with biospheres to try to simulate all of the conditions that are necessary for us to have self-contained, just ecological conditions. And the lengths of time we're talking about within any foreseeable type of propulsion technologies, it's so extraordinarily complicated. Not to mention just think in terms of human civilization as we know it existing for 10,000 years. And we're talking hundreds of thousands of years of travel. And so this is, my suggestion is that we actually think about space travel from a multi-generational perspective so that we can understand, first and foremost, we have to secure our home base. We have to actually make sure our own spaceship is healthy enough so that, because it's perfectly attuned to everything we need and we get it free, more or less. And so if we can really take seriously that is not separate from our desires to get into ships and go to other places, that we can begin to look at what would a 1,000-year, a 10,000-year strategy look like for human space exploration. And I think that could yield some extremely interesting conversations around where we are now and where we want to go.
So I think for a lot of us, we can't think past next week.
Well, precisely. We're kind of trained to think in terms of quarterly profits, and it's hard for us to think beyond 10 years from now. But this is why I think the inspiration of space could actually be the catalyst that we need. In my experience working with a lot of these data sets, it expands people's imaginations to such a scale that they kind of pop at a certain point, and that's a good thing. We really need to have that ability to be, our cognition visually responds to that level of complexity, that level of scale. So, I think it's a really important thing for education to be inspired by what our visions might be for the future.
Okay, so let's have
wonder if I could speak to
that
that briefly. I think the important point that David just made, and correctly, is that we're not going to solve a crisis on Earth by moving somewhere else. So we're going to have to solve our local problems locally. But you interviewed Anusha Ansari earlier today, and she said that she would sign up for a one-way trip to Mars. And I think the key phrase there is one way. People, sooner or later, the technology will become possible for people to take trips that plausibly might last hundreds of thousands of years. They'll be one-way trips. They won't be civilization changing. It'll be small groups of people. They'll probably have wacko leaders, charismatic groups. But the technology will be inexpensive to the point where small groups like that could set off and say, well, we'll just find something. They'll be the wanderers. And we'll forget about them almost immediately, because they'll be lost to us.
Well, we did a poll at the session this morning, breakfast session this morning, and I guess there were, about 30 people, 40 people in there? Of those, 3 people in the room would go on a one-way trip to Mars. So let's just repeat that poll here while we're at it. First of all, just get a sense of, if you could put your hand up if you want to go into space. Yeah, so it's a good number of... I've always wanted to be a train driver rather than an astronaut.
We're in space. If I
okay, yes, we're in space, so we can do that. So there was about half. So who would go on who here would go on a one-way trip to Mars? Sign up for a one-way trip to Mars? I don't see any. Is there any hands?
There's one.
Oh, well, yeah.
Yes, right.
God, that's really interesting, isn't it?
Yes.
Yeah, okay. Right, let's have some other questions, please. If you can put your hand up really high and sort of wave it around, because we're a little bit dazzled here. So this gentleman here. Just wait for the microphone to get to you, yeah.
Sorry. In the vision or the presentation, you talked about dark energy and dark matter, which, to my understanding, are relatively new concepts, very well accepted today. But they're all theoretical concepts in that we haven't yet, as far as I know, shown that they truly exist. And so how likely is it that our view is not going to change again and that maybe we won't include so much dark energy and dark matter in the future.
Okay, I'd like to contradict, if I may, a little bit of what you said. The evidence for dark matter is more than theoretical. We've got abundant evidence for gravitational forces acting within galaxies and clusters of galaxies that can't be accounted for by the matter that we add up, that we see. So there's some extra matter there, or the forces of gravity are beyond our present comprehension. So there's a great deal of theoretical work involved in dark matter, but it rests on observational data. Dark energy, in some sense, is also it's a theoretical concept, but it rests on actual observations of the expansion of the universe. The rate of expansion is observed to be accelerating, and we interpret that theoretically with this concept that we call dark energy. I'm actually very much an optimist scientifically. I think within 10 or 20 years, we'll have a very good idea what the dark matter is made out of. I don't think we're likely to make any progress in my lifetime on what the dark matter is made out of. The dark energy will remain mysterious, I'm convinced.
But you're fairly certain that model now we have of the universe and the way it was formed, that will stay? It won't. That was your question, really, wasn't it?
Is the model going to change?
Yeah, is it going to change?
I don't think so.
No.
There are lots of observational support for it.
Okay, and I'm sure Newton said that as well.
Fair enough.
Can I have another question? Yes, up here. If you could keep your hand up, that's excellent. Thank you.
So on all the items that we're looking for in colliders and so on, are they like the Higgs particle, that all these things we read about in the paper, are they part of the 5% of the known universe, or are they part of the 95% of what we don't know about yet? Or is that even a reasonable question?
It's a very good question. So far, everything's part of the 5%. There's a hope, a reasonably well-founded hope, that particles will be produced at CERN in the same experiment that are actually close analogs or possibly even representatives of particles that make up the cosmic dark matter. But that hasn't happened yet.
Okay, let's have another question. This lady down the front here.
This is a question for David. You shared with us the current model of the solar system, and it just blew my mind. And I'm one of the mega dorks, and I've never seen that. And I think that model has the potential to revolutionize anything from spirituality to environmental concerns to future projection. Where can we get that and see it and share with people that we care about or want to influence in some way?
Sure. Well, the funny thing is that model was made by a DJ for his rock video, for his music video. And I've had extensive conversations with physicists that specialize in celestial mechanics around why we don't see that more. And it apparently has to do with the two-body versus a three-body problem and the predictions and everything. So this model is for illustrative purposes only, and that there's a lot of things that can be said about being not quite scientifically accurate about it. What I'm astonished about, though, is that we continue to use the flat, static sun model more than anything. And you can go online, there's a site called djsadhu.com, and you can also look at the Bad Astronomer if you Google this I think it's called the helical model, where he gives a breakdown of all the things that are wrong with it. But the irony of that is he doesn't do a breakdown of all the things that are wrong with all of the models of the solar system on all of the NASA sites with a static sun. So I think that this notion of the sun not being static, and it is one of those sort of Copernican moments, right? When I've shown this before, and people are astonished to realize that the sun is actually moving at these incredible speeds, and we are having all of these dynamics going on all around the place, that we can see these kind of helical patterns echoed all around us. And so I think that it's important that from a visualization perspective, we really start to explore the implications of that. And there have been some progress lately. We're showing one particular film in the dome here called Cosmic Collisions that the Hayden Planetarium did. And they do that to some degree. They don't make a very big deal out of it. But I do think it's an extraordinarily profound realization to understand that those are closer to the dynamics of the solar system that we understand.
Okay, so I have another question. Any from this side? No, you're all very quiet on this side. Right in the middle.
Thank you.
take us out 5 minutes. You take us out 3 billion years. Take us out 5 minutes or 4 minutes. What kind of species is going to be around here in 25,000 years when we come to the Aspen Institute?
Hopefully not the same one.
Either of you want to tackle that question?
I think we're going to be laughing at ourselves. I think we're going to be watching these videos. Well, actually, probably won't, because all the formats will be long,
And the lead
relegated
still won't work.
to the realm of, CD-ROMs. But we'll have stories of what we believe the world to be, and we'll be laughing at ourselves. And then at some point we'll realize, oh, wait a second. 25,000 years from now, we'll be laughing at ourselves again in another 25,000 years. So that's what I would speculate.
I mean, how do you get your head around this big sort of...
I'm not sure that any of us really get our head around it. But it's actually where mathematics really does save us, is that the level of abstraction that math gives us allows us to talk about distances and timescales that are so unimaginably larger or smaller than our human scales that we become familiar with them without really being, you might say, at some sort of visceral level wrapped around them.
But you reckon there'll be a stage here in Aspen in 25,000 years' time?
25,000 years? Oh gosh, I don't know.
It's great, no one knows the answer to that one.
But I do think the visceral level saves us from the abstraction of the mathematics sometimes. Mm-hmm. I mean, that in trying to visualize these things, that it really does help us reflect on what our assumptions are going into all of this. So it's this nice dynamic interplay that constantly happens, because working with a lot of scientists and coming at it from an artistic perspective, I'm astonished at the degree of abstraction that can occur. And even anyone trying to wrap their head around the LHC, it helps tremendously to the Large Hadron Collider. It helps tremendously to be able to try to put that into some perceptual form, because it's critical that I think that people start to comprehend what's going on there, because it is so extraordinarily abstract for most people.
Okay, let's have another question. Yes, on this side here.
In the 60s, if you wanted to get away from Vietnam, you went to Canada. And immigration has been a part of the American story for a couple hundred years. It's in the press. You've now shown us that there's no way to leave this planet. So
you could still go to Canada.
So if, in fact, there are all these things swirling around in space that man has put up, and the environment problem and population, you've told us how long it's taken for life to evolve. How many decades, years, centuries before life extinguishes here based on mathematics of what's happening with aerosol cans, with spaceships, and with population explosion?
So how long we got, basically, before we have to...
See that we can't go anywhere else.
Yeah.
Well, I'd like to make a concept. I think life is extraordinarily resilient, but humanity is less resilient. So we might mess our environment up. We might very well mess things up so badly that we don't make it. But there'll be microbes, there'll be insects, and if we're lucky, there might be voles and weasels and small birds left over, and then things will gradually come back. So I think there's very little risk that we'll destroy carbon-based life altogether. But absolutely, for all the reasons that we're concerned about, we might do some real harm to the alpha species.
But in pure astronomical terms, we've only got it's about 2 billion years, isn't it, till we wouldn't be able to live on the Earth.
Because of the 2 billion.
2 billion. So we'd have to do this. We'd have to get off in some form.
Well, so let's consider the evolution of Homo sapiens, right? So this is I tend to think in terms of there's a lot of scalar fallacy going on. Like people get angst-ridden over 2 billion years, and we can't even imagine 100, right? So there's this extraordinary lack of communication about what we're talking about a lot of times. And so I think when we're talking about things like human civilization being around for a while, that's very much up to us. That in order to, these aerosol cans aren't just manufacturing themselves. The red list chemicals in this building aren't just magically appearing. We're making design and engineering decisions to create toxic environments. And we have the option of actually not doing that. And increasingly, as people are realizing the actual condition of humans on Earth with all of our microbiomes and everything we're dependent on this planet, it's actually a pretty good deal for us to use our imaginations to start thinking about how to create an economy and a civilization that's much more restorative and regenerative than trying to fantasize about how we're going to build capsules to get off the planet. It's way more economically sane to think about it this way. And one of the things that we do at the Buckminster Fuller Institute is sponsor a challenge every year where we give away money, and we put out calls for projects designed to make the world work for 100% of humanity in the shortest possible time through spontaneous cooperation without ecological offense for the disadvantage of anyone. Right? And it's happening. I mean, people are actually doing this stuff, and it's incredible what our imaginations can allow us to do. But I do think there's so much angst around all of these existential threats coming around that we tend to just take the easy path out and think, well, technology is going to save us somehow. But it's very much about our own agency, about how long we really want to be around.
Okay, we've got time for, I think, one more question. Yeah, this gentleman down here.
Right before Carl Sagan had died, he talked about a sort of evolutionary glass ceiling for humanity where we exceeded our capacity as mature individuals by creating technological advances that were far beyond our ability to grow as a race. Do you guys have any thoughts on that and how that applies in your search of the cosmos?
Charles?
I'm much more optimistic than Carl was. He got a little dark towards the end there. But he was a great imaginative scientist. I think we're going to somehow pull through all of this. I just don't know how yet. And I think it'll be a combination of things of the kind that David's talking about. And actually, I do have quite a lot of faith in technology because every now and then innovations really do make a huge difference that's positive. I just don't know how it's going to happen. As for a glass ceiling for humanity, one point that David just made is that, we're recently on the scene in evolutionary terms, and there's no reason to believe that evolution stops with us, right? In fact, we're probably beginning to develop the technologies to channel that evolution in ways that we might find scary in the future. So there's going to be, all I know about the future is going to be very different from what we see around us now.
David?
I mean, again, I think it's so much about our own agency, and that sometimes these challenges seem so complex and daunting that it's easier to sometimes just say, well, it's sort of in the cards, and this is our fate. But I'm too much of a pragmatist to spend too much time in that speculative realm. I mean, I think the things that inspire me and why I love working with this work and why I love working in education is I see people in the world that are doing things that are so unbelievably unaccomplishable in terms of how they're learning from ecosystems, how they're creating designs and structures that are starting to resuscitate a lot of things that have been killed, a lot of things that have been destroyed. And so I think it very much depends on your perspective on whether we're just passive observers within this entire system, or we're actually active agents so that we can begin to design a world and understanding with all of the science and technology. You're absolutely right. I mean, technology plays a huge role in it, but I don't think that it's got any particular trajectory in and of itself.
Right.
It's our agency that's going to determine how that technology gets applied. So those types of absolute statements, I don't know, I just don't understand them enough to have any kind of opinion on them. I like to see models that are working, and those are way more interesting.
Well, I think we've probably raised more questions than we've answered in this session. Thank you very much for coming. Thanks my speakers, David and Charles.
Thank you.
Right. Really good.
Nice one.
Right.